Researchers at MIT have made significant steps toward creating robots that could practically and economically assemble nearly anything, including things much larger than themselves, from vehicles to buildings to larger robots. The new work from MIT's Center for Bits and Atoms (CBA) builds on years of research, including recent studies demonstrating that objects such as a deformable airplane wing and a functional racing car could be assembled from tiny identical lightweight pieces, and that robotic devices could be built to carry out some of this assembly work. Now the team has shown that both the assembler bots and the components of the structure being built can all be made of the same subunits, and the robots can move independently in large numbers to accomplish large-scale assemblies quickly. The new work is reported in the journal Nature Communications Engineering. A fully autonomous self-replicating robot assembly system capable of both assembling larger structures, including larger robots, and planning the best construction sequence is still years away. But the new work makes important strides toward that goal, including working out the complex task of when to build more robots and how big to make them, as well as how to organize swarms of bots of different sizes to build a structure efficiently without crashing into each other. As in previous experiments, the new system involves large usable structures built from an array of tiny identical subunits called voxels, the volumetric equivalent of a 2D pixel. But while earlier voxels were purely mechanical structural pieces, the team has now developed complex voxels that each can carry both power and data from one unit to the next. This could enable the building of structures that can not only bear loads but also carry out work such as lifting, moving, and manipulating materials, including the voxels themselves. The researcher says that while earlier versions of assembler bots were connected by bundles of wires to their power source and control systems, what emerged was the idea of structural electronics, of making voxels that transmit power and data as well as force. Looking at the new system in operation, there is no wires, there is just a structure. The robots themselves consist of a string of several voxels joined end to end. These can grab another voxel using attachment points on one end, then move inchworm-like to the desired position, where the voxel can be attached to the growing structure and released there. The researcher explains that while the earlier system demonstrated by members of his group could in principle build arbitrarily large structures as the size of those structures reached a certain point in relation to the size of the assembled robot, the process would become increasingly inefficient because of the ever longer paths each bot would have to travel to bring each piece to its destination. At that point, with the new system, the bots could decide it was time to build a larger version of themselves that could reach longer distances and reduce the travel time. And even bigger stretches might require yet another such step, with the new larger robots creating yet larger ones, while parts of a structure that include lots of fine detail may require more of the smallest robots. As these robotic devices work on assembling something, they face choices at every step along the way. It could build a structure, or it could build another robot of the same size, or it could build a bigger robot. Part of the work the researchers have been focusing on is creating the algorithms for such decision making. The software they developed allows someone to input a shape and get an output that shows where to place the first block and each one after that, based on the distances that need to be traversed. The researcher says that there are thousands of papers published on route planning for robots, but the step after that of the robot having to make the decision to build another robot or a different kind of robot, that is new. There is really nothing prior on that. While the experimental system can carry out the assembly and includes the power and data links, in the current versions, the connectors between the tiny subunits are not strong enough to bear the necessary loads. The team is now focusing on developing stronger connectors. Ultimately, such systems might be used to construct a wide variety of large, high-value structures. For example, currently the way airplanes are built involves huge factories with gantries much larger than the components they build. Similarly, the researchers says that in producing a new car, you can spend a year on tooling before the first car gets actually built. The new system would bypass that whole process. Such potential efficiencies are why these researchers have been working closely with car companies, aviation companies, and NASA. But even the relatively low-tech building construction industry could potentially also benefit. While there has been increasing interest in 3D printed houses, today those require printing machinery as large or larger than the house being built. Again, the potential for such structures to instead be assembled by swarms of tiny robots could provide benefits. And the Defense Advanced Research Projects Agency is also interested in the work for the possibility of building structures for coastal protection against erosion and sea level rise.